Hello everyone and welcome to the ANSYS tutorial. In the today's session, we are discussing shear force and bending moment of a cantilever beam which is fixed at one end and a load of 10 kilonewton is acting at free end. So the problem description is compute the shear force and bending moment diagram for the beam shown. Assume rectangular cross-section area of 0.2 meter into 0.3 meter. Young's modulus is 210 GPa and the Poisson's ratio is 0.27. So 10 kilonewton is acting at free end. The length of the beam is 5 meter, which is fixed at one end. Let's move to the theoretical calculation. So first we need to calculate the shear force. So for my calculation purpose, we are pointing this load section as A and B. This section is B and this point is A. Since we have one load at B and one load which is fixed fixed end A, so we are making two division here. So shear force at B, first you need to calculate. We know that shear force is the sum of the movement or sum of the loads towards the left or right of the section. So we need to add all the loads which are acting on the beam. So shear force at B point, a load of 10 kilonewton is acting. So we are taking this direction as positive. So 10 kilonewton shear force at B is 10 kilonewton. You can see. Next, we don't have any points in between B to A. So next we have to move to the point A. In point A, there is no any extra load acting. So since the shear force is the addition of the loads, so already we have 10 kilonewton load at B, which is same which will be followed to A. So in A there is no extra load is acting. So shear force at A also we have 10 kilonewton. If there is any extra load acting, then you have to add that load. There is no extra load acting at B, so the shear force at A also will become 10 kilonewton. So next, the bending moment. So the bending moment is nothing but the multiplication of load into distance. In case of shear force, we are taking only load, but in case of bending moment, we have to multiply load into distance. So bending moment at B, so this point B is 0. Why? Because one point we should know that the bending moment is always 0 at free end, because at free end we have load of 10 kilonewton but since the bending moment is the multiplication of load into distance, so load is there 10 kilonewton, but from 10 kilonewton to B distance is 0. So anything multiplied by 0 is 0. So 10 into 0 is 0. So the bending moment at free end is always 0. Next, we don't have any point at from B to A. So next we need to calculate the bending moment at A. So at bending moment at A, we have to calculate what are the load acting till A. So we have only one point load acting at B, which is having a distance of 5 meter from A point. So 10 kilonewton is having a distance of 5 meter from A point. So the bending moment is multiplication of load into distance. So the bending moment at A is load into distance. So the load is 10 kilonewton. The distance of this load from point A is 5 meters. So the bending moment will become 10 into 5. That is 10 into 5 minus we are taking for bending moment. This kind of load, this direction we are taking as minus. If there is a opposite load acting as this direction, for that load we are taking positive. So minus 10 into distance is 5 meter. That will become 50 kilonewton meter. So our unit always we take it in Newton dash millimeter. So convert this unit into Newton per millimeter. So kilonewton to Newton we have to add 10 raised 3. For meter to millimeter, again we have to add 10 raised 3. The total will be 10 raised 3 plus 10 raised 3, 10 raised 6. 50 into 10 raised 6 Newton dash millimeter is our maximum bending moment, which is at A. This is about the theoretical calculation. Now let's prove it in ANSYS. Let's move to the ANSYS. Go to preferences, structural, okay. Then go to preprocessor, element type, add, edit, delete. Click on add, go to beam 2D 188, you have to select, click on OK, close this. Now go to material properties, in that go to material model, structural, linear, elastic, isotropic. Enter here the Young's modulus, which is 210 GPa, which is nothing but 210 e raised 3. The Poisson's ratio is 0.27. Click on OK. Close this. Now go to section. Now to give the section here, go to section beam. In that go to common section. Now enter breadth as 200 millimeter, which is given in the problem, and height as 300 millimeter. Click on OK. Now go to modeling, create key points in active CS. Click on first node number, apply it as 0 0 0, all three directions 0 0 0. OK. Apply, click on apply. Now second point, which is having a distance of 5 meter, x distance is 5 meter. So I will enter, instead of 5 meter we have to take in millimeter, so I will write 5000 millimeter. Click on OK. The two node is created, key points are created in the screen. Then go to the create lines. In that lines, again go to lines and straight line. Select the two key points, first key point and second key points. A line is created. Click on OK. Now go to meshing. That size control, go to size control, manual size. That go to global. That size, click on size. Click on edge length. It has 10 and this as 100. Click on OK. Now go to mesh. Click on lines. Click on pick all. Now meshing is done. To see the meshing, you go to plot lines here. You can see the meshing here. Now meshing is over. Now go to solution, apply load here, solution, define load, apply structural, and go to displacement. On key points, select this key point. Since this node is fixed, this end is fixed, click on OK. Select all DOF, click on OK. So everything is fixed here. So next go to the force moment load here. In that define load, go to force moment. On key points, select this second key point, click on OK. Now change the direction as FY, and this you have to give us load is 10 kilonewton, so which is acting at a minus negative direction. So 10 into e raised 3, 10 kilonewton is nothing but 10 into 10 raised 3 Newton. You have to give the load in Newton. So click on OK minus, because the direction is reverse. You can see the direction. If you give positive, the load will take in this direction. This is wrong. So you have to give negative direction, Fy, and in negative direction. So the load condition is over now. Go to general post processor. Before that, you have to go for solve current ls. Click on OK. Solution is done. Close this. Then go to general post processor. Then go to element table, define table, add by sequence number, Here you have to select SMI SC, write it as comma. This is for generating shear force and bending moment diagram. Click on apply. Then again you have to go for by sequence number. Click on 6. Again click on apply. Again go to by sequence number SMIC. Click on right, enter 16 here. This time apply. Now again go to by sequence number SMIC. Now write 19. Click on OK. 3, 6, 16, 19. Everything has come 4 points. Click close this. Then go to plot result. In the deformed contour plot, that go to line element result. Now for generating shear force diagram, you have to make node I as 6 and node J as 19. Click on OK. You can see the shear force diagram minus 10,000, which is exactly same as our theoretical value. This is the shear force diagram. Then go to click on again line element result. Now change the node as 3 and 16 for bending moment. 3 and 16. Click on OK. You can see the bending moment, which is 50,000, 50 into 10 raise 6, which is same as our theoretical valuation. So we have compared both the theoretical and ANSYS values. So that's it for the today's session. Thank you.